So today we're going to talk about cylinders, quadric surfaces, vector value functions, and space curves. The cat this is Ember. This is my cat Ember. A drawing I have of her. Just copy and paste it from one session to the next. But yep. Anyways, so cylinders. We got the classic circular cylinder, and you can tell you have an equation of a cylinder if in R3 if you're missing a variable. So if we have like x squared plus y squared and we have no z squared and it equals some radius, say 1, then the fact that it's missing z that's what makes it like parallel to all the rulings, parallel to the z-axis. And so one way to kind of draw these is first look at what variables you do have, right? We have x and y. And so I'm going to create an x and y axis in 2 dimensions. And then I'm going to just go ahead and graph it like it's in 2D. This is the unit circle in 2D. And then to make it 3-dimensional, I notice there's no z. Well, that means it's going to look like this picture for every plane z equals k. Every plane z equals k, we're going to have this trace or impression left on the plane. And so imagine the z-axis is right here, sort of like sticking out of the page. Like if you were to stab your pencil at the origin and have it sticking towards you out of the screen, then that would be the z-axis, like right here. And so yeah, this is a cylinder, right? Cylinder that we all know and love. So now we have the notion of generalized cylinders, cylinders that don't take this normal circular shape, and I'll show you one. So missing a variable. Oh God. That means you got a cylinder. So I'm going to give you an equation. Z equals x squared. This is a cylinder with rulings parallel to the y-axis. And so first I'm going to draw the trace. Now the trace, right, I have x as the independent variable and z as the dependent variable. And we just have a regular parabola, the parent function parabola. Okay, but now for every plane, y is equal to k, where k is a real number. We're going to have this impression left on the plane. Now, so the y-axis would be like right here. If I was to stick my pencil right here and sticking out of the screen towards me, that would be the y-axis. And so let's go ahead and transfer this to 3 dimensions. Okay, so we got the y, we got x, we got z. And now, so on the negative x, we're like kind of engulfing the z on either side, you know, right? On the negative x, we're shooting up, and on the positive x, we're shooting up. So it's going to look something like this. And then it's going to look like this all the way across. Right, and these are the rulings, these are the lines that are parallel to the y-axis. So you kind of get the idea, right? It would have been easier if I had picked the plane z equals y, because that's just more natural to draw based on how I drew the axes. But yeah, we get the same parabola for every slice of plane on the y side. So this is like, you know, y equals k. And so this plane, slicing it, if we were to shift it this way and turn it towards us, we would get this picture. We would get a parabola. Cool. So yeah, this is a cylinder, a generalized cylinder, because we're missing the variable y. So now we're going to talk about quadric surfaces. Let's see, where's my... So quadric surfaces. It's going to be easier if you recall your conic sections from pre-calculus. It might have been a while, but all of the traces of all these, the next 6 equations I'm going to show you, all the traces can be reverted to a conic section. Now, why they call it conic sections, right? It's conic, because you take 2 cones that have been inverted, or inverted on top of each other. So we got one cone, and we got like another cone right here. And so where conic sections actually come from is if you slice this shape with planes, right? If we slice it with the plane across here, then we flip it towards and see what impression it gives. What would be the impression of this this shape onto the plane? What line would I have drawn? It's a parabola. Very good. Let's see. So you would have something like that. And then, right, we have the special case if we have the plane slicing through right here, right through the very center of it. That shape would just be 1 point. But if we go up or down any, and we keep it horizontal, then that would be a circle. Now, if we rotate this up any and have it slicing like this now, then we would have an ellipse because it would be like oblong on one side. And if we go vertically like this, through the top and the bottom, we would get hyperbolas. Okay. So the following quadric surfaces, we got ellipsoid, ellipsoid is x squared, a squared plus y squared, b squared plus z squared over c squared equals 1. Now notice what happens if I let, say, I don't know, any of the variables equal 0. Let z equal 0, for instance. We have the what this is looking like on the xy plane if z equals 0. Then we would be left with x squared plus y squared over a squared over b squared equals 1. And graphing this on the xy plane, let's see, we would suppose a is greater than b, then this distance would be a, this distance would be b. Sort of like a football or whatever. So that's where conic sections are going to come in handy. To know the length of the major axis right here, the length of the major axis is 2a. The length of the minor axis is 2b, right? Because you just take the square root of whatever is on the bottom. And you could do a similar thing if you would like let x, so you say we wanted to let x equal 0, then we would have y squared plus z squared, right? And then suppose we have, you know, the y-axis as a horizontal one, z-axis is vertical, and then, you know, say this time let's have c being greater than b. It would look like this. Yeah. One cool thing about these, you know, quadric surfaces, or one thing you don't have to worry about that we learned about in about conic sections is like the foci, for instance, the foci right here, the focus, this one and this one, 2 points on the interior. You don't have to worry about that, right? And in this case, or for any of these, like you would with you know, in a pre-calculus class. But you know, just drawing a rough sketch is good enough. Now, we got paraboloid next. Let me, I guess, draw a picture of what this ellipsoid might look like. So I draw down here. We got z, y, x. Let's see, I made a greater than b and c greater than b. So if we do this, oops, I do the negative axes as well. Okay, so a, b, b, and c is greater than b as well. So then we have so that's the xy trace, and then we draw our height to come up to z and back down, and the other side as well. So it's like a sphere, only it's longer on the z side, on the x side now. So yeah, rough sketch. Doesn't look too pretty, but gets the point across. So next we have paraboloid. Infinity on the x-axis. It doesn't shoot out forever because well, this is the equation I'm graphing right here. This is the equation I'm graphing. Yeah. I see what you're saying. No, I wasn't graphing this one. Yeah, in 3 dimensions, that would go in the x direction forever. Yeah, you're right. It would be an elliptic cylinder at that point. Yeah, if we were to graph this in 3D, that would be an elliptic cylinder. But I was graphing the ellipsoid. Sorry if I didn't make that clear. Now we have paraboloid, elliptic paraboloid. We got z over c equals x squared over a squared plus y squared over b squared. So whatever variable doesn't have the square, right? You set it up, you just try to mimic this as best you can, right? Sometimes you might have like x over a is equal to y squared over b squared plus z squared over c squared. Well, then we know that it's going to be like engulfing the x-axis at this point, right? Because with this picture, it's engulfing the z-axis, right? We have parabola, parabola, and then the other trace would be a parabola as well, but I'm not going to draw it. And then it's just like kind of eating up the z-axis. Over here we have it eating the y-axis or the x-axis. So we have this is harder to draw than on paper for me, but yeah, that looks ugly. Anyways, yeah. For instance, we'll get to an example. I guess I should show that right now. So okay, let's hit an example. So we got this equation. All right. So to get this into the standard form for a paraboloid, we have to complete the square. So I'm going to group all the y's. And I'm going to group all the z's. We move the x to the other side. I'm going to keep the 20 right here. Okay. So what number goes in this spot if I'm completing the square? It's always, and when you're completing the square, yeah, so when we're, there's good algebra to know. So if we have like, x squared plus bx, it's 4. It's always, you do b over 2 squared, and then this will give you, well, we have -4 over 2 squared, which is -2 squared, which is 4. So that's just how you complete the square. And then when you put it into the completed square form, it's always the b over 2. So we got b over 2 to be -2 right here. So it's going to be y minus 2 squared. But since I added 16 really because this is 4 times 4. So I also have to put add 16 to the other side. Now it's the same number, right? -4. So we just follow this b over 2 squared, -4 over 2 squared, -2 squared equals 4. Yeah, we'll get it canceling, right? Because then we get 4 right here, and then we get 16 plus 4. So this is 20, and this is 20 right here. So these cancel nicely. Okay, so now we have 4. We have 4y. Oh, I can't see my cursor. Where'd it go? Okay. 4y minus 2 squared plus z minus 2 squared equals x. Now, so it's kind of like the x-oriented, but we have a shift this time, right? So the very tip of the paraboloid, since I don't have a plus or minus over here, this is like a -0, for instance, you know, we have x being 0, y being 2, and z being 2. X being 0, this is the x-axis, y-axis, z-axis. So we got 1, 2, 1, 2. So the tip of my paraboloid is right here. And then this 4 right here, it makes it so that we have smaller y input will send it further back in the x direction. Because there's a scaling, right? It's 4 times, and then we have like a smaller number in here than over here. Well, this is gonna, you know, make it, this is gonna blow it up a little bit. So we get this paraboloid. And now that's a horrible picture. So, but we could look at the traces, you know, we could look at the traces where, and then divide by 4. Yeah, you could. However you want to do it, yeah, you want that C right there, then you could do, you know, y minus 2. That would be good actually for, yeah, because then we have z minus 2 squared over 4 equals x over 4. Yeah, and then check this out. Let x equal 4. So that means we're 4 units out on the x-axis. This is the plane x equals 4. And then we're going to look at the impression left. We have y minus 2 squared plus z minus 2 squared over 4 equals 1. What is this a picture of? What does this equation mean? What shape is this? No, it's just an ellipse. If we're looking at the trace, yeah. If we're looking at the trace of x equals 4. So the trace x equals 4, right? We have some plane, and then we have y-axis. We have z-axis. Well, okay, so this is like over 1, so we go 1 in the y direction, and then this is 4, so we go 2 in the z direction. Let's say it's right here. And so this is like kind of the cross section. So that's what I was trying to draw right here, like this ellipse right here. And then we just have ellipses all the way down. For every plane x equals k, we have an ellipse for positive k. Yep. So draw traces to show, if you're not the best 3D artist, to show that you do know what you were talking about. And it was good to pick x equals 4 so that we got a 1 right here. And then it was just an easy, no more manipulation after that. And they were nice round numbers. Okay, so that was an example you might run into. Give you some monster of an equation, and then you have to complete the square and do some algebra until you get it into a work form. Okay, so we got ellipsoids, we got paraboloids, and now we're going to look at cones. But you've already kind of looked at cones, but we have the equation now. It is like it's like the paraboloid, except for the z is squared now. So almost the same, except for the z wasn't squared with the paraboloid. Z is squared with the cone. That's how you can tell the difference. And so this would look like here, like this, and like this. And then we have the same sort of traces as we were talking about before. Vertical traces being hyperbolas, horizontal traces being ellipses. Yeah. So cones not too hard. Now we got hyperboloids. Let's see. We got hyperboloid. Of one sheet. So hyperboloid of one sheet, the equation looks like an ellipsoid, except for we have one minus. So we might have something like x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. This minus is what it's the axis it's engulfing now. It looks like we got what are the horizontal traces? What shape are the horizontal traces? If I was to draw a horizontal axis based on this equation right here, circles. Oh yeah, parabola or not parabola, ellipse. Because we're assuming that A and B are different. If A equals B, then the horizontal traces would be circles, but they're ellipses right now because it's the general form. Cool. And so I might draw it like it's a circle because that would be just easier. So we got circles all the way up for every slice that we make, but it looks like this. Sort of like a tornado or something. Really weird shape. Yeah, this is a hyperboloid of one sheet. Now we got a hyperboloid of two sheets. That is if we have two minus signs. So suppose we have negative x minus y plus z. We only have one plus sign. So it's going to engulf the z-axis this time. And they look like this. And the best thing you can do is just graph them on Geogebra, honestly, and just look at what they look like and try to draw what that is, what you see. If you can't draw it using the traces, if you're looking kind of wonky or whatever, and you want to know what it looks like, go to Geogebra, free 3D graphing, and you can get nice pictures of all these conic sections and more. And then we got one more. We got hyperbolic paraboloid. And I'm not going to even try to draw this one. The equation would be z over c is equal to x squared over a squared minus y squared over b squared. So we can see if we do horizontal traces, like suppose z equals c, then we would have what shape or what conic section? C over c is equal to 1. That's a hyperbola. So all the horizontal cross sections are hyperbolas, and we got parabolas for the vertical traces. Okay. So now I got some questions similar to the homeworks, and we can try to do them. We can see what they look like. So example. Use traces to sketch and identify the surface. Okay, now we have, let's see, negative x squared plus 4y squared minus z squared is equal to 4. What quadric surface is this? What surface is this? Yes. Hyperboloid of 2 sheets, because you can tell because there's 2 minus signs and every component is squared, or every variable is squared. So what we're going to do, how to draw the traces, first I'm going to divide by 4 so I have it equaling 1. We have minus x squared over 4 plus y squared over 1 minus z squared over 4 is equal to 1. Now let's do the let's do x equals 0. Right? We get x equals 0, that term cancels. Then we get y squared over 1 is equal, or minus z squared over 4 is equal to 1. Okay, now I'm going to have the independent variable being y and the dependent variable being z. That's just how I choose to do it. This is a hyperbola. Now, what coordinates are the vertices at? Which coordinates? What are the coordinates of the vertices? And does it like engulf the y-axis or does it engulf the z-axis, right? These are questions. This is all from pre-calculus. So engulf the y-axis, yeah, that's correct. So what's the vertice? What number is this? It's 1, because we took the square root of 1. Yep. And so this 4 right here, it has to do with like some point up here. Because like you would draw a box. If you really want to get deep into the conic section, and then you have these lines, and then it would like approach these lines like asymptotically. And then it would, this 4 would also determine where the foci are. because this would be 2, 0 right here, or 0, 2, and this would be 0, negative 2. But that's kind of irrelevant. You just want to know the general, what it looks like. So yeah. Yeah. Yes. Now let's do the other. Let's do z equals 0. So we got what we got? Negative x squared over 4 plus y squared over 1 to 1. Okay. So this also engulfs the y. Right? It's still a hyperbola. But it engulfs the y. It's the same picture, really, but just flipped. We have 1, 1. Okay. And so now transferring this to 3 dimensions. Here we go. Let's see. It's a hyperboloid of 2 sheets. And we have vertices at, let's see, 0, 1, 0, and 0, negative 1, 0. And then we would draw our hyperboloids. Yeah. Cool. Now let's see. We got one more example, and then we're going to go on to vector value functions and space curves. And the example we have 8 plus 2y equals, or 2z equals negative y squared. So solving for z, we get z equals, divide everything by 2 and then move this 8 over. We have negative 1/2 y squared minus 4. And so drawing this as y with the independent variable in 2 dimensions, and z, so we have minus 1, 2, 3, 4 shifted down 4 units. And this negative 1/2 just makes it a little bit wider. So what shape is this in 3 dimensions? What shape is this in 3 dimensions? In 2 dimensions, the xz plane, we have celery stick. Yeah, it is. Wow, I never thought about it. That is a celery stick. It's a parabolic cylinder. Yeah, a celery stick. That makes sense. Nice. So then graphing, we have see, 4. We go down, down, and then it stretches. Did I draw that wrong? Yeah, I did. Ruling's parallel to the x-axis because x is missing. Oops. And then, so we got like that, and then it's going this way, parallel to the x-axis. Yep, so a celery stick. Okay. Let's see, we got vectored value functions now. So a vectored valued function is given by r of t equals f of t, g of t, h of t, which is also could be given by f of t I hat plus g of t j hat plus h of t k hat. Now, just a couple preliminaries. Yeah, preliminaries. So if we have the limit as t approaches a of r of t, this is equal to the limit as t approaches a of f of t, limit t approaches a g of t, and the limit t approaches a h of t. Just apply the limit to each component. Nothing too complicated. I mean, it's like you just have three functions now, and for each, one in each component. One variable makes it a curve in space, but the three components make its ambient space R3. Now, similar to the limit definition of continuity for a function of a single variable, we have the vector value function R is continuous at A if the limit as t approaches a of r of t equals r of a. That is, if the limit equals the function value, then we have continuity. Now, that's the same thing from calculus 1. Okay, let's look at an example of a vector value function. Describe the curve defined by the vector function. We have r of t, drum roll, 1 plus t, 2 plus 5t, negative 1 plus 6t. What is this? How would you describe this curve? Someone describe me this curve. It's a straight line. See, we've done this before. Putting it in parametric form, we have x equals 1 plus t, y equals 2 plus 5t, z equals negative 1 plus 6t. So the lines we were dealing with in the previous sections were vector value functions. Now we might get some more complicated components now, but yeah, so the parallel to vector. What vector is it parallel to? What's its slope vector? Yeah, 1, 5, 6. Perfect. Oops. All right. Okay, now we got a cool example to look at. That was just to get our feet wet. Now let's sketch r of t equals cosine t I hat plus sine t j hat plus 2t k hat. So as far as the x and y components are concerned, that's the I and j components, it's the unit circle. That's how you parameterize the unit circle in R2. Because cosine squared, we got x squared plus y squared equals cosine squared t plus sine squared t. This always equals 1. That's the Pythagorean identity. So as far as x and y are concerned, we just parameterized a circle going this way. You can check that it goes this way by plugging in values. But we're going to plug in values as well for the 2t. That just gives it height. That gives it the z component, and it travels in z linearly because this is t to the first. So now let's just get a couple points going. We have r of 0. What is r of 0? Perfect. Okay, now what should we do next? R of what value? Pick an easy one. The most natural, pi over 2. There you go. That's what I would have said. Pi over 2, and we get 0, 1, pi. R of pi equals -1, 0, 2 pi. R of 3 pi over 2 equals 0, -1, 3 pi. R of 2 pi equals 1, 0, 4 pi. Okay. So now we got a sketch. So these have direction to them because you can look at t as time. Time t equals 0, we're at this point. At time t equals pi over 2, we got 0, 1, and then pi. We go with pi units. Let's just make it like that. This is 1, this is 1. And so we traveled up right here. Okay, now at t equals pi, we traveled up to 2 pi, and then we're on the negative side of x. So you can see it's like a staircase, it's going up. And then we got 3 pi over 2, we got -1, we got 0, it's a helix, yeah, that's what you call it. That's the name of it. And then finally back up. So, and the helix, it would live on a cylinder. So you could draw a cylinder, and then the helix would be like the spiral up this cylinder. And the 2, it just gives it more rise. This 2 gives it more rise. You could have a 4, you could have a 1, you could have a 1/2. Squish it if you want. Okay. Now let's look at an example. Okay. 2 particles. So as the coefficient of z approaches 0. Wait, hold on. I can see it this way. So as the coefficient of z approaches 0 infinitely, but it never touches it, would we get a cylinder? Yeah. Yep. You would. That's cool. Yeah, if we had like cosine t plus sine t. And then we had this is I and this is j. And then we had some like limit expression, the limit as t approaches 0 of t, k. Well, then we would gain like an infinitesimally small height every time. And so it would be circling around like this. But yeah, that's a cool idea. Okay, so we have this example: two particles travel through space along two different curves. Will they collide? They may intersect, but will they intersect at the same time? That's the key. At the same time, they have to have the same XYZ coordinate. So I'm going to give you two vector value functions. R1 of t equals t squared 7 minus 12 t squared. R2 of t equals 4t minus 3 t squared 5t minus 6. Will they collide? If they do collide, at what time? So they'll collide if x, y, and z are equal at the same time. So we set x equal to x, y equal to y, z equal to z. And then we solve. We got t squared minus 4t plus 3 equals 0. We got t, we're factoring this. We got a negative 3 and a negative 1 equals 0. So t equals 1 and 3. Over here we got t squared minus 7t plus 12 equals 0. Factoring this, we got t, negative 4, negative 3 equals 0. T equals 3 and 4. Over here we got t squared minus 5t plus 6 equals 0. We got t minus 2, t minus 3 equals 0. So t equals 2 and 3. Okay. Wow, we got a 3 in every one of these. So what I'm going to do, say R1 of 3, R2 of 3. R1 of 3 is 9. So you got 21 minus 12, because 7 times 3 is 21, minus 12 is 9. And then we got 3 squared is 9. R2, we got 4 times 3 is 12, minus 3 is 9. You got t squared is 9. We have 15 minus 6 is 9. So at time t equals 3, the xy components, xyz components are all the same, thus they collide. Okay. We're gonna do a couple examples, and I'm gonna use some graphing capabilities that gives us some really cool pictures. And this next problem is about parameterizing. If we have two surfaces and they intersect at some, it would be a curve. They intersect at a curve. How do you parameterize that curve? How do you get a vector value function that represents that curve of intersection? So find a vector function that represents the curve of intersection of the two surfaces. And we got the surface z equals 4x squared plus y squared. And then we got y is equal to x squared. What type of surface is this? The z equals 4x squared plus y squared? It's a paraboloid. What surface is this? It is actually a cylinder. It's a parabolic cylinder. A parabola is a curve. I asked what surface. A parabolic cylinder. Okay. So this equation, equation 2 right here, 2 is a function of x. Y is a dependent variable. So from 2, I'm going to let x equal t. Then that implies that y is equal to what? If I plug in t, I get t squared. So now we have x is equal to t, y is equal to t squared. Now what would z be? Well, z, plugging in x and y, I get 4t squared plus t to the fourth. Yep. Okay, so my vector value function, r of t, is equal to t squared, 4t squared plus t to the fourth. Sweet. So now, hopefully I can do this without messing up. Okay, I'm going to share a different. All right. So when I go to Geogebra, I always go to these settings right here. I go to settings, and for the x, y, and z, I put show positive direction only because it just is less confusing. So that example that we were just looking at, we have the paraboloid. The cylinder, and the curve of intersection parameterized. You can do parametric in here. So it looks like we did it correctly. That's right. Math can be fun. It is. It really is. So I also just wanted to show you guys something really cool. So I found a cool parametric function right here. And we can show that it's on the surface of a sphere. Isn't that something? That was x equals the square root of 1 minus 0.25 cosine squared 10t times cosine t. Just it's a tomato. Yeah, that's right. So this parametric curve lies on the surface of the unit sphere. And And looking at the equation, it kind of looks like something similar to spherical coordinates. So maybe something of that from the origin of it. So you guys got any questions? The secondary function. This one? The secondary surface. Like the first one, the line was intersection of two surfaces, or the two surfaces on this one. Oh no, this isn't. This parametric that I have graphed right here, the black line, is not the intersection of two surfaces. Well, it might be, but I don't know what those surfaces are. Yeah. So a use of parameterization is finding the curve of intersection, but not every parametric surface is a curve of intersection. This one just happens to lie on the unit sphere. Yeah, it does. It does look like that. It reminds me of the polar equations, right? Did you ever play around with those? A cardioid looks like a heart, and you can get some like flower petals going. Yeah. So, let's graph the helix because we have some time. So we got, I'll show you how to type it in. Just parenthesis, cosine t, comma, sine of t, comma, 2t. Let's just do t over 2. Yeah. And then let's change the t value. Let's do 10. Yeah, so it goes up a little bit higher. Now we can let's make this t now. Yeah, man. See you guys later. Y'all have a good one. You're welcome. See you guys next week.